So thank you all for coming to this NPA seminar. And so to begin, I'll hand things over to Evan Kraft, who will introduce today's speaker.
So I'm introducing, I wrote something to introduce. It's my pleasure to introduce Bruno Scheihing-Hitschfeld for Yale. Bruno received his PhD at MIT, working with Professor Krishna Rajagopal, who's part of the work today. He's currently a postdoc fellow at the Kavli Institute for Theoretical Physics in Santa Barbara. He has worked on a variety of topics ranging from early universe cosmology, which I didn't know about myself, to heat transport and disordered materials, and he is currently interested in the physics of hot QCD matter. Bruno is a three-time Olympic champion, back-to-back four-leaf clover collecting king, and tied for #1 postdoc award in my heart. Today, he will tell all of us about how heavy quarks propagate through the quark-gluon plasma.
Thank you. That's a very, very kind introduction. Okay, well, thank you for being here. I'm really happy to be here to tell you about some recent work with Krishna Rajagopal and Urs Wiedemann on probing quark-gluon plasma with heavy quarks, so understanding how we can get information of quark-gluon plasma using heavy quarks as probes. And because I know I have a broad audience today, I'll try to define everything I'm doing and start explaining first what quark-gluon plasma is. And for that, I'm gonna just do a brief analogy with something entirely different, which is water. So if you know that if you put the water molecules in a box and heat them up or apply some pressure, you'll see different phases of matter emerge. You get a phase diagram depending on pressure and temperature, solid, liquid, or gas. And the question that you can ask is, what happens if I just take the fundamental building blocks for a universe? If I take standard model matter and I apply similar extreme conditions, what do I get? This has been a research program for quite some time. And the answer, at least in terms of QCD, is this phase diagram we see here on the right, conjectured in many ways. But it's the thing that we want to understand when we say quark-gluon plasma. So at low temperatures and low varying chemical potential, we have a hadron gas phase, which I'll mostly not talk about today. And then at high temperatures, we get a quark-gluon plasma phase of deconfined QCD matter that we're interested in exploring and understanding. So this phase diagram, I have to say, it's a bit old by now. You'll see you'll see some features of it that are outdated by now. One of them being the conjectured position of the critical point. Now, if this plot were remade today, it would probably that critical point would be pushed to the right. The energy scan 2 is over. So that's just to say that there's many interesting things to look at in this diagram. What I'm going to do today is talk about heavy quarks, so charm and bottom quarks in quark-gluon plasma, so in this high temperature phase of QCD, over the zero varying chemical potential line. So I'm just going to be focusing on how a heavy particle propagates through a hot medium and seeing what it does. The plan of my talk is to first motivate how we can think about heavy quarks as Brownian particles moving through quark-gluon plasma, and how, as a theorist, I think this takes place in heavy ion collisions. Then, as a theorist, I'll tell you what I would actually calculate to describe this process, and with that, go on into the actual framework of how we could connect that calculation with data eventually. So I'll start reviewing what people have done a lot over the past couple of decades in terms of Fokker-Planck equations, which come from studying heavy quarks in the non-relativistic limit. And then I'll introduce a new framework that we've been developing, which is a more general case that applies to the non-relativistic limit as well, up to larger momentum of heavy quarks. And the main feature that you have to take into account, that I'll explain in great detail later on, is that in the relativistic case, you really have to take into account that the momentum transfer from quark-gluon plasma to the heavy quark is non-Gaussian rather than Gaussian, as you could assume in the non-relativistic limit. And I'll go through that in details if it's not clear, transparent at the moment. And then I will do something that the theorists in the audience will appreciate, well, will enjoy, because they all have in their hearts this theory, N equals 4 super Young-Mills theory, which has the advantage that it provides us with a gauge theory that has some similarities to QCD, where we can actually do the calculation of the object I'm interested in. And I'm going to show you how the world would look like if we run heavy quark equilibration with these results, and show you essentially how to take those results and use them as a form of gaining intuition for what QCD is doing microscopically. So first item on the schedule, Brownian motion. Brownian motion I think of it as, or you can think of it as, a heavy particle moving through some fluid. So here I'm gonna play a video of a heavy particle being kicked around by some smaller particles that compose a medium, and it will move randomly around in a way that's characterized by the properties of the medium. And essentially, this isn't moving. Essentially, what one does in order to characterize this random motion is to write a stochastic equation for how this heavy quark moves. So you write Newton's law. The force acting on the heavy quark will be some random force given by how this fluid fluctuates, and those fluctuations will both make the heavy quark lose energy and also give it fluctuations, eventually leading to the heavy quark thermalizing with the medium. You can do this in quark-gluon plasma as well. That's the main point. So in quark-gluon plasma, we don't have I would not draw a kinetic description like the one I drew just now in terms of billiard balls, let's say, scattering off each other. But you can still think of a heavy quark as being randomly receiving kicks from the medium, being moved around through some stochastic force that we would like to characterize and understand how this heavy quark loses energy and diffuses around. And well, this is not a theoretical exercise. This is something that you can, wow. There's more animations like that. And you can think of this process as happening in the middle of a heavy ion collision. So a heavy ion collision, well, you have two very highly Lorentz contracted nuclei that collide. A plasma is formed. That plasma evolves driven by pressure gradients, expands, cools, and eventually these particles free stream to detectors where you all measure what is seen. So for my interests today, what I want is to discuss how these heavy quarks will propagate in this in this phase here of quark-gluon plasma that takes place between 1 Fermi and 10 Fermi, and this cartoon of how a heavy ion collision takes place. So all of what happens after the system hadronizes and particles free stream to the detector will not be today's topic, but rather I'm going to assume that I have heavy quarks propagating through already equilibrated medium and try to ask questions about how that dynamics unfolds. So I'm going to draw this image there again, and I'm going to zoom in. Wow. And I'm going to say, as a theorist now, I'm going to prepare a state with a heavy quark with momentum p. This, by heavy, I mean it's much bigger than the temperature in a medium at temperature. No, the temperature is T. And then I just want to ask, if I let some time T pass, what do I get at the end of the day? I'll likely get a heavy quark in a different momentum state, and I would like to characterize that momentum change probability. How does this change from P to P minus K is determined by the dynamics of the theory that the heavy quark is interacting with, in this case, the light degrees of freedom of QCD. And of course, this will be a complicated object. It depends on the momentum that the heavy quark had, the temperature of the medium, the time it propagated through the medium, and every other possible scale in the medium. So this list here is not a comprehensive list down here. But nonetheless, we this is the object of interest for this kind of problem. And if you sit down as a theorist and try to write a formal answer, not doing calculations, just formulating what you need to do, it's actually not too difficult to come up with a formal expression for the momentum change probability. So loosely speaking, you use heavy quark effective theory to calculate the amplitude to go from between different momentum states. Then you take the square of that amplitude, you average it over a thermal medium with a temperature 1 over beta here, this grand canonical partition function. And in the limit where the quark is heavy, you can use heavy quark effective theory to write this probability in terms of the Fourier transform of the expectation value of a Wilson. And as a theorist, in principle, that's all you need. Now you have to sit down and do a calculation, which people have tried, and we're only one more instance of that long list. That being said, of course, this object is somewhat complicated. It's not an object that is under good control in perturbation theory. So you'd really like to use some non-perturbative methods to evaluate it. And after you sit down and try to think for a while what you can do, the first question you end up asking is, do I really need to calculate the whole thing? Could I just do something simpler? Because this object here depends on two vectors: the heavy quark velocity and the spatial separation between those two Wilson lines. So you have a 6-dimensional object that looks complicated. So let's start somewhere. Could I just take some features of it and see what I get? And the intuitive answer is yes, that you should be able to do it. If you go to the non-relativistic limit, you can think of a slowly moving heavy quark being kicked around randomly by particles in the medium. And if you're in the non-relativistic limit, you can argue essentially that the collisions with the medium are basically identically distributed. You can use the central limit theorem to say that if you wait long enough, all of the momentum transfer will look Gaussian. Even if the microscopic P of k is non-Gaussian, after you repeat a sufficient number of times, you'll end up with a distribution that is characterized by a mean and a variance, which would be the drag coefficient, so the mean force the heavy quark experiences, and the diffusion coefficient that tells you how much its momentum fluctuates. So you would just say, I don't need the full P of k, I just need its mean and variance. And if you do that, you then would take that momentum change probability, write down a transport equation, in this case a Fokker-Planck equation equivalent to the Langevin equation I have up there, and say this is my equation in a static brick. You can add dynamics to the hydrodynamic background as well that I'm omitting throughout the talk for simplicity. And then you can ask, what do the dynamics, what are heavy quarks driven to? And there's a theorem called the fluctuation dissipation theorem that tells you that these two coefficients are actually not independent. They're related in this very precise way, kappa equals 2m T times the drag coefficient. And this guarantees that if you write this equation, the late time solution will be a Maxwell-Boltzmann distribution. So heavy quarks will reach local thermal equilibrium with the bath if you're in a thermal medium. So that's all very nice. And people indeed have calculated this heavy quark diffusion coefficient in many ways. You can do a perturbative calculation of what this looks like in QCD. You can take the theorist's favorite theory, n equals 4 Young-Mills, and do the calculation also at weak coupling, but at strong coupling here as well, where you again get a result. There's lattice QCD calculations of this object that, if you can see, very nicely lie in between the strongly coupled limit and the weakly coupled limit at high temperatures. So it seems we have a pretty good picture of how diffusion takes place of of a heavy quark inside a thermal medium. So sounds great. Why am I giving this talk? It sounds like people in 2006 had pretty good control over this process. And the reason why we need more is because if I go and look at data, I look at RAA for d hadrons, so the number of these that I get in a lead-lead collision normalized by the equivalent in a PP collision, you'll see that data goes from, in this plot here, from 0 to 50 GeV. In this other plot from CMS, well, this one prefers by Alice, the second by CMS, goes somewhere between a couple GeV and 100 GeV. And if you think about what the charm quark mass is, it's 1.2, 1.3 GeV. So if I am telling you that I have a heavy quark moving through the hot medium that is quark-gluon plasma forming heavy ion collisions, and I want to use this Brownian motion picture that I just introduced to you, I really need to be away from the non-relativistic limit. I need to go, even if I don't want to go all the way up to where you can start thinking of jets. Even if I am at, say, down here at 4 or 5 GeV, you could still ask the question, well, is my non-relativistic limit making sense? Or do I have to do something more? And then you can say, well, I had a nice equation that gave me a nice solution for how heavy quarks equilibrated. But if the heavy quark is moving, then these transport coefficients might depend on the momentum of the heavy quark itself. So you would just take the equation I wrote down earlier and generalize it a tiny bit, saying that now the drag coefficient depends on momentum and the momentum broadening coefficients also depend on momentum. And you will have one in the transverse direction, one in the longitudinal direction, because now you have a preferred direction. And then you can ask, will this equation drive heavy quarks to local thermal equilibrium with the bath, with a quark-gluon plasma? And just examining this equation, you'll see that equilibration requires, again, a relation between the diffusion coefficient and the drag coefficient, in this essentially substituting what was before the mass of the heavy quark with the energy of the heavy quark, and it's the longitudinal coefficient, diffusion coefficient, the one that appears. And so, okay, still looks good. And this relation is guaranteed at low momentum because we have the fluctuation dissipation theorem. However, if the momentum is non-zero, then there's no theorem enforcing this relation. So you can take one of two approaches. One is you take this as an assumption if you really like the Fokker-Planck equation that I just wrote, and just calculate one of these, either kappa or eta, and fix the other one in terms of one of them. Or you could go and try to calculate both and see if the approach is good or not. And there's where the problem comes in. If you do the calculation of these two coefficients you take a quantum field theory, but either weakly or strongly coupled, you'll see that as soon as the velocity of the heavy quark is non-zero, then the variance of the kicks that the heavy quark receives and the mean force it receives are not related in the way that you would need for them to reach equilibrium with the bath. So this is both a theoretical and a practical problem, because if you want to put together a simulation from which you can extract numbers that you would in principle calculate in QCD, you need that the equation you feed into that simulation to respect the features of the theory that you started from, QCD in this case. And the generic case in quantum field theory is that this does not happen. You can then you could still do it. You could plug this equation and try to fit data with it, but then you run into the issue that now you no longer know how to connect these numbers with quantities that you could calculate in QCD, in principle. So if you want to use data to extract QCD properties, something that I can come here as a theorist and say, this measurement gives me this constraint on this non-perturbative expectation value, I have to do more. And this is not a mild problem. Like if in the theorist's favorite theory in N equals 4 super Yang-Mills, this ratio of the diffusion coefficient over the other side of the equation that should be 1 grows with the Lorentz boost factor as gamma to the 3/2. So already at gamma equals 4 or 5, you get an order of magnitude of separation between the number that you get and the number that you should get. So we do have to calculate the whole thing. We do have to examine what happens in more generality if we want to get conclusions about QCD from heavy quark transport. So then back to the chalkboard. Now, instead of Gaussian stochastic process, now you'll have a more complicated stochastic process. I promise the next 3 slides are the heaviest in terms of equations, and then I'll go back to figures. You essentially take you take the probability, the momentum change probability, and you update the distribution in discrete time steps. You take the limit where that time step is small, and you get a highly nonlinear, highly arbitrarily high order in derivatives partial differential equation that you know how to define from QFT in terms of this expectation value, but it might be complicated to solve. Then you can first ask, does this solve the problem that I presented just now? Does this actually lead to kinetic equilibrium? And the answer in short is yes, you can non-perturbatively prove that this equation derived from this non-perturbative object actually guarantees that equilibration takes place. This is the last thing, this is the last result we got in the previous paper with Krishna and Urs, that essentially this symmetry relation of the time evolution operator, therefore the distribution function, is the non-Gaussian generalization of the Einstein relation I told you earlier. And it means that if you do an honest calculation in a QFT of that object over there, you will get sensible answers. If you like Markov chains and statistical methods like that, you can also show that this equilibration condition is equivalent to the statement that this momentum change probability satisfies a detailed balance condition around equilibrium. And this is an example here of one such distribution that I'll come back to later, as it is the result of a calculation. And just showing that it can be highly non-Gaussian. As you can see around the maximum that's represented there with a blue dot, energy loss and energy gain are highly asymmetric. So in summary, not in summary. So once you have that, you will take that evolution operator, which is complicated. And since you're doing a calculation in large mass limit, you can use the T over M expansion to simplify that equation into a nonlinear yet first order in partial derivatives, and which still guarantees that equilibration takes place. So in what follows, I will just play with the simpler equation and show you how what the dynamics looks like, what heavy quark transport properties one can probe, what one can see in the dynamics that follows from here, and eventually, essentially, what I'll comment on what features of K we would like to extract. Okay. Any questions so far before I?
So is that equation the Kolmogorov equation?
Yes, this, I mean, the general term for the differential equation that comes from stochastic processes is a Kolmogorov equation. There's actually, if I go into the terminology, you'll have Kolmogorov forward and Kolmogorov backward equations, and that's a math distinction that I'm not going to go into.
No need.
So is P a 3 momentum vector or a 4 vector?
It's a 3 momentum vector. It's a phase-space distribution.
So, I mean, I can see how Brownian motion and this go together, but what if you have a change in virtuality of the heavy quark?
Yeah, no, this is all on shell. This construction takes on shell heavy quarks, and virtuality is neglected here in all of what I'm showing. So before running the equation, I have to tell you what to use here in place of K. And for that, I go to n=4 supersymmetric Young-Mills theory, where we did a calculation and we got some nice results extending what people had done 20 years ago.
Sorry, the plot that you showed earlier was n=4 then, or
The
P of K?
yes, but I didn't tell you that then. I'm gonna tell you that.
Okay, good.
So first you can ask why should I do calculations in n=4? And this is something good to remember from even from a broader perspective. Why do we look so closely at this theory, which is not QCD? And the first reason, which is somewhat simple, is that we want a QFT where we can do calculations reliably at strong coupling. And n=4 is one such example. And because QCD is strongly coupled, then we do the best we can. Then you can ask, do we get anywhere close to what you measure in experiment? And in heavy ion collisions, at least, you can ask various questions about a couple of observables. Here I'm going to mention two. Observables, quote unquote, in the sense that it's not something that I can directly read off data. Bayesian analysis is needed to extract with assumptions of what the dynamics is in between. But still, you can compare a prediction from this supersymmetric theory, plugging in reasonable numbers for the hydrodynamization time. In this case, this is the time it takes for right after the collision, the quark-gluon plasma to become hydrodynamic. So how long is the out of equilibrium stage where the system is still thermalizing as a whole? In n=4, you get a prediction that's going to be between 0.1 and 0.7 Fermi. And if you do the Bayesian analysis along the trajectum collaboration did a couple of years ago, you get 0.3 Fermi. So again, right ballpark. Shear viscosity, a famous result from n=4 that and holography in general, that this ratio of the shear viscosity over entropy density should be 1/4 pi. You compare that with the number that you would extract from a Bayesian analysis on data. And again, it's not 1/4 pi, but it's slightly above 0.1. So at least this theory is not doing anything crazy. It is reasonably close to what is happening in the real world in heavy ion collisions. So what is this P of K? This P of K is is the one I showed you earlier, where we managed to do the calculation in n=4 at strong coupling from the non-perturbative expectation value that I have on top up there. And this is the one example where I know this calculation has been done at strong coupling. Of course, it would be very nice to do this in QCD, either at weak coupling. There's not that much. There's still things that could be done in weakly coupled QCD that haven't been done. Ideally, one would like a truly non-perturbative termination in QCD, which would require, as far as we have right now, lattice QCD input. And but as a side remark, this is a real-time observable. And lattice QCD has a famous sign problem with that. So so that is not at least immediately possible. So given that that's the situation, we're going to play and see we're going to take this result and play with it and see what we get for heavy quark dynamics in a finite temperature medium. So you can start from 0 velocity and increase the velocity and see how this momentum change distribution looks. At zero velocity, you have a distribution that, even though it's non-Gaussian, you can calculate its variance, and you can check that it matches the old calculations. You can see it's rotationally symmetric between longitudinal momentum transfer here and transverse momentum transfer. And then as soon as you turn on a velocity, you see that this distribution quickly becomes skewed. You have a tail that decays much more slowly towards towards positive energy loss than towards energy loss than energy gain. So this KL here has its sign defined relative to energy loss. So it's more likely to lose energy than to gain energy. That's all that this asymmetry is saying. And you can then look at this and start characterizing it in terms of moments. You can, so the blue point up here is the drag coefficient, the most likely value of the force the heavy quark experiences, and that in holography is just characterized by well, in n equals 4, which the calculation proceeds with holography. Is characterized by this number here in front of the momentum, essentially, over the mass. And the variances you can also calculate, and they grow with the Lorentz boost factor in different ways. And if you keep going, say you go to v equals 0.99, the distribution becomes more and more skewed, and the maximum gets pushed more and more to higher momentum transfer. And you can do this all the way to, you can plug in any value of the velocity, and the nice thing is that we have explicit analytic expressions for this function, for this 3D function here. They're not so simple that I would write them on a slide. Well, they are on an extra slide if you want to have a look at it. But it's not something that you can look at and say, yeah, obviously this function looks like this. It's they're special functions with, well, they're hypergeometric functions with which they make it so that you can't just read that off. But when you plot it, it looks.
Sorry, you said this is more likely to gain energy.
It is more likely to lose energy. So K is defined with positive sign for energy loss and negative sign for energy gain. Are somewhat arbitrarily, but so that the most likely value.
I get confused with the sign.
Yeah, so that the most likely value is that is positive. So, great. We did a long calculation. Lots of effort for that. Can we say something that makes this interesting in terms of phenomenology? And this is ongoing work. So I'll show you some figures of what the dynamics that comes out of here looks like. So the first example you can consider is, imagine you initialize a distribution of bottom quarks in a static brick of strongly coupled plasma at a temperature of, say, 200 MeV. So I'm taking a ratio of mass over temperature equals 20. And I'm gonna start with a very occupied distribution around some high momentum scale. Well, in this case, P over M equals 20 or so. And I'm gonna ask how, if I plug the result from n equals 4 super Young-Mills, I use it up there for that time evolution operator K, and I run the dynamics, and I get what the phase space distribution of heavy quarks looks like at later times. You get some dynamics. The heavy quarks stop, they get pushed to lower momenta, and at late times they go to the curve that you would expect from thermodynamics. You would get the the relativistic Boltzmann distribution. So the energy is not just p squared over 2m, it's the square root of p squared plus m squared. And so you can do this, and you can do this all the way from fairly relativistic energies all the way down to equilibration. Then you can ask, okay, that initial condition is clearly meant to illustrate how a lump up here equilibrates. What about something more realistic? So if I initialize the heavy quark spectrum with something that you would expect in heavy ion collisions. So in this case, this is a phonal-like initial condition. So the perturbative production cross-section of heavy quarks, fixed order next to leading log, I believe, that we have put in here by hand, or rather a curve that looks very close to that. And the blue curve is an initial condition. Here also compared with what the equilibrium solution is, so just a Boltzmann distribution. And again, evolve these heavy quarks in a static brick of strongly coupled plasma, this time for a mass over temperature ratio of charm quark-like. And you see that first you equilibrate at soft momentum, and then you start equilibrating at hard momentum in a way that somewhat preserves the nature of the initial condition at high momentum. So you see that even though the occupation is going down, the slope is more or less unchanged. And the interesting thing to look at is essentially the point at which the distribution changes from being equilibrated to still dominated by the perturbative cross-section production.
Sorry, if I let it run for even longer, it would eventually equilibrate, or?
Yeah, it will eventually. Yeah, eventually this line will continue to go down, and this line. Yeah, there's a log scale, by the way. So, but for all practical purposes, at the end of this plot, it's perfectly equilibrated because this is 10 to the minus 6.
I see.
This is just showing off that we can do it. And even with a cutoff up here, because you don't expect to produce heavy quarks at arbitrarily high energies, of course. Okay, so then, did I make any progress in understanding how these what these figures look like? So for that, let me first define the closest thing I can calculate with this approach that should tell me whether I'm close or far. So if I want to study medium modifications of this of heavy quarks in this theory, what I would do is just simply take the number of heavy quarks that I have at a given time with momentum p. By the way, all of these distributions that I'm showing you are spatially isotropic. So I'm even making one more assumption that we don't have in heavy ion collisions, which is there we have a preferred axis. And taking the ratio of that to the initial condition, essentially counting how many more or less quarks I get at a given momentum because they propagated through a medium. And the theory curve you get in this theory looks like this. You get that very rapidly a minimum is generated, and then essentially the curve grows to both sides, and I'll go into more detail why that is in a second. This is a calculation at the purely partonic level, if you want, in a static brick, so there's no hadronization, there's no cold nuclear matter effects, there's no hydrodynamic medium. It's a very simple-minded theorist's calculation, with the fact that we have done a very careful treatment of how the interactions of the heavy quark with the medium. So then, well, you can also look at this in terms of snapshots and already see that this looks good, in terms of generating some minimum at a scale that is between 5 and 10 GeV, and then a growth to the right. So you can go here, take the data, give the disclaimer that the data, you can think of it as a snapshot of heavy quarks having gone through the medium with some path length and stopping the dynamics at some time. Of course, this is an average over many such events where, I mean, the path length is not always the same. There's hadronization, there's also hydrodynamic fluctuations. So the comparison is not apples to apples, but as a theorist, I can still play the game of checking how far off am I. And for the intermediate momentum range, it's not bad.
Sorry, this is for supersymmetric Yang-Mills.
Yeah, the blue curve is supersymmetric Yang-Mills. It's a theory with no mass scale, not QCD. And it's only answering the question, how does a heavy quark lose energy to a thermal environment?
Looks pretty good.
Yeah, I mean, it looks good in between here, and you'll see that on the two sides, something is missing. Like both at low momentum and at high momentum, this is not doing, this is not perfect by any means. At low momentum, the reason is somewhat straightforward to understand, I guess. It's because I'm doing things in a brick. I'm not doing things in a flowing hydrodynamic medium. So at low momentum, the effects of flow will be larger on the heavy quarks. So this curve, so the curve here has really no hope of lying directly on top of data. And at high momentum, what happens is that the fluctuations in this strongly coupled theory are actually much larger than in QCD. And this, you can say words that this is due to asymptotic freedom, but because in this strongly coupled theory, you're strongly coupled at all scales, so you don't have suppression of interactions at high momentum. And it turns out that the fluctuations are so large that there's small but non-negligible probability that you'll be pushed forward rather than stopped. So that's why you get the growth on the other side. You can also do this on top of the Alice plot. And again, you'll see the same that I showed you before. So you'll see that at low momentum, this is not yet there because I don't have flow effects at least. And at high momentum, you'll see that this grows faster than what data is actually doing.
I have one question is, does the minimum depend on the mass?
Yes.
So then you have some predictions for say.
Oh, I haven't tuned it here. I could play the game of like tuning what the mass of the charm quark is and try to extract an effective mass in medium. But
instead of if I do charm if I do bottom, then you have expectation of what
Yes, I have plots that I could show you.
And then also the time, you have to cut off the time.
Yeah, of course, I have to select a snapshot of this. Like I have to tell you what's the expected path length. And
does that actually jive with
and if I estimate what the path length where this curve is here, this is about 4 Fermi. So take it with a grain of salt. It's a different theory. Just the fact that I got the order of magnitude more or less right, it makes me happy. And again, this here on the left isn't, if you want to use it for phenomenology, it's still incomplete. We still have a list of things that one would need to add and well, to make this more realistic. But as a baseline to understand how heavy quarks are stopped and equilibrate in a way that in a single framework connects the low momentum regime with the higher momentum regime, where at some point you might want to start talking about this in terms of jets directly, with the perturbative picture that we have from perturbative QCD, where as opposed to this strongly coupled picture where I am not scattering with any individual constituent of the medium, just scattering that with a strongly coupled environment collectively, and see what we get. But this is very good motivation to try to understand how this would take place in QCD, and even just take it as it is and see if you can characterize the evolution operator that I introduced earlier that is directly tied to a quantity that you can calculate from first principles QCD and see what you can learn.
Sorry for the previous slide. The one right before this.
Yeah.
Am I supposed to freeze? So when this evolves in time, am I supposed to freeze it in my head at the time that you say on the next slide?
Yeah, you can.
I should freeze it.
You can freeze it here.
It's not. I mean, it's not bad. I mean, it's for supersymmetric mills. I mean, that's not bad. That's pretty good. Like even for the last plot. I mean,
that's up to you. Like I agree. I'm very happy that this is close, but it's still a different theory. So
it has a lot of qualitative features.
Yeah. yeah, I mean, as a theorist, I'm very happy. No doubt. If I want to tell you, then you can ask the inverse question. Okay, since this is close, then probably the evolution operator I wrote down here is not that far from what you would write for QCD, and then you can start constraining what this operator actually is in QCD. Grain of salt. Yeah, so that's it. We clearly, I think, have good reason to pursue this further and try to understand how we would constrain this type of non-perturbative expectation values in actual QCD with data. To do that in a complete way, we'll have to include more features to this. We'll have to, into this framework, we'll have to add a hydrodynamic background. We'll have to include hadronization effects. But so far, it's looking good. And there's also things to do on the QCD side. So we would like to know, even if it's complementary and not, even if the curves will not lie on top of each other, what will weakly coupled QCD tell us? There's plenty of work to be done, even theoretically, just here. Can we get some input from lattice QCD as well? This is also something that would be very interesting, and because then you have two handles that you're very sure about and try to test your theory understanding in the middle, and then from there go on and ask, did we miss anything in the rest of the physics? Is this all that's going on, or can we, or are we missing something conceptually? And that's that's how we learn. So thank you.
Thanks for the amazing talks, and maybe we can. I guess we ended a bit early, so we have time for questions.
Yeah, thanks. I really learned a lot from this talk. I think I do have a fundamental misunderstanding that it would be helpful if we could clear up really quickly. So if you go back one or two slides, where you develop this minimum in the ratio of the later time over initial time, where you have like a high hiccup of a tail and high momentum. I'm trying to square that the previous plots you showed, where you start with the funnel-like distribution, and it falls onto at low momentum onto this one onto the equilibrium solution. But to me it looked like, and I think you said a comment to this effect, that at high momentum the distribution isn't really changed much.
Well, look, but I mean that's
it's
the
a log
thing.
log,
Even a small change here will give you something visual.
So I should be able to.
So if you look at here at 100. And in for the first time step, it will actually move up.
Yeah. Okay. I just, in my memory, it didn't move a lot, and
so in the first couple of time steps, this goes down and this goes a bit up.
So
that's why you get. No, I'm literally taking this curve and taking the ratio of itself.
I was understanding. Okay. Great. Thanks.
More questions for Bruno.
Can you show me MB?
Can I show you?
The hadron.
Oh, B hadrons. I don't think I have the plot.
Or like how it depends on.
I can show it to you on my laptop. I don't have them on the set of slides.
But which direction does it shift?
Oh, to the right.
I can ask you a question. So you kind of alluded to this in the beginning of your talk, but you have this picture of these heavy forces interacting with these statistically things. But of course, you've shown us that strongly coupled gang mills kind of happen to data, and we know that the quark-gluon plasma in terms of Kavli particles may not be the best picture. So you alluded to this in your talk, but what is the correct picture to think of this? I don't want to use Kavli particles.
I mean, you don't have, in this strongly coupled picture, you don't have it. So this is another argument for why you should trust this kind of calculation. But this is not a no-go theorem that you can't get this with quasi-particles. This is just showing you that I did a calculation where I didn't tune anything, basically. I just plugged in numbers that seemed reasonable and got curves that look reasonable. But I mean, it's, you can try to do the calculation, like, this is what I alluded to at the very end, like, you can try to do this calculation in a weakly coupled theory as well. And then try to see the differences, like, will you get something dramatically different or just marginally different?
What is the at strong coupling? What is the picture of a heavy quark diversity? What do
I mean, you're interacting with collective excitations, let's say. You still have dynamics, it's just that you can't, if you look at 2-point functions of things that would be particles in a weakly coupled theory, you will not see peaks centered around a dispersion relation. So you will not see some preferred relation between momentum and energy.
some smear?
You'll see something smeared that will propagate doing whatever the theory wants it to do.
Oh, can you put up your summary?
Yep.
Maybe I missed it. Very naive question. It's about hadronization. How do you get from a charm quark to compare to the hadrons in the RAA plot?
And what I showed here,
Yeah.
I'm neglecting that completely. I'm not doing it. I'm not keeping track of any fragmentation or any type of hadronization effects. I'm just showing you the bare work.
So how does the charm quark end up with the same momentum as the D quark?
Doesn't.
I think I remember seeing somewhere in the plots that these calculations are at mu equals 0.
Yeah.
Is there, I guess, any way to include baryochemical potential, or like what would
Yeah.
that look like?
So yes, and I don't think anyone has done calculations like this of finite chemical potential. But yes, you at least at the formal level, you can add a chemical potential to your partition function and see what it does.
Do you expect it would change the curves much?
In this strongly coupled limit, I don't expect a big change. But that's a bit. Yeah, but I can't. But don't take that too seriously, because this is only from the intuition I have in this strongly coupled supersymmetric theory, which for which it's anyways not straightforward to define a chemical potential. So in terms of QCD, I wouldn't expect it naively to do much, but I would like to see a calculation to be confident about it.
The slide 61. I had a question. I might not remember it. If I don't, we can just stop.
Yeah.
Yeah. So I was trying to read through some of these back of the envelope figuring here. So the gamma nuclei for the two different cases. My question is, I guess you get a similar hydrodynamization time from the two, but using seemingly very different gamma factors for the nuclei in the two cases. How do you? I guess I'm wondering. You're getting to the same thing, but is it still the same physics if you're getting there in a different path?
I mean, if you boost this a bit more, you'll pull this a bit down. Yeah. This is. Yeah, I somehow went over this too quickly, and then this can be run, like you can do this estimate at 1400, and you'll get a slightly smaller number.
Okay.
I mean,
so it goes in the direction.
I mean, it's very, like you can read it off here. This is 5. W goes inverse of gamma. If you push this up by 1.5, you'll 0.5.
Okay, so it actually helps the agreement. Okay.
Yeah.
Maybe we take 2 more and then we can disperse.
Can you go back to the input from N equals 4 super young? The theory is like
in this, or
so the input is only this expectation value of the Wilson law.
Yes,
and that was computed before, or you had to compute
this. We computed it in this work and earlier this year.
And could you explain a bit what it is? It's some Wilson loop.
Yes, I can, but knowing your background, I think we can take this offline.
Yeah, we should do that. But I guess like it's a very like broad, like I guess I don't understand exactly what it is, but could you do like some effective string computation for this? It depends on which regime it is, but then it would be closer to PCD.
So you'd have to, so the string would have to start at a heavy quark and be broken at being coupled to some light quarks from the medium. So it's not it's not just a string coupling the two heavy quarks. Like if actually I have pictures, these are pictures in the holographic setup, but so
It's a string theory in our lab. Really, we got broad set of.
so yeah, so you can think of it like this. You have in holography at least, you have two strings each hanging from one Wilson line into the bulk, and they meet not at any intermediate point. They meet at the horizon, which is essentially the point where you are coupled to the bath. So if you try to do this in field theory, you'll have to. You won't have this higher dimension. You'll have to couple this end to something else, and given that the physics here is that of the thermal bath, that's where you would have to be. Yeah, I would be happy to chat about that, but
Sounds like the answer is no, not easily. So
no.
thanks.
Let's take one more if there's one more lingering. Someone's heart, they'd like that. Don't make me ask. I will just ask one final thing. So just to be clear for everyone. So your comparisons to data, you've taken into account no Haitianization effects, nothing complicity. It's purely just a comparison of what you get in speech
Yeah, I mean, this is not. I would not call this a comparison to data rigorously.
What you have.
This is a plot of the bare parton level individual heavy quarks between some snapshot of the in medium evolution at some time and the initial time. Data is measurements on hadrons at your detector. And in between, a lot happened. In particular, these heavy quarks hadronized and either got together or fragmented into objects with different momentum, which was modified by whatever it hadronized with, either with a medium or something, or you create whatever. So it's not. So this is it's not even an apple and an orange. There's an apple and there's a car. There's many physics here. There's a lot of physics here.
Your blue curve,
yeah,
is just.
A blue curve is an apple at most.
I think that's impressive. How about we give